So your the one problem from problem set 4 is due today, but there won't be another problem set assigned today or next week because we have an exam coming up, and so that exam again is going to be in the evening. I'll bring snacks. From 5:30 to 7 p.m. in room 190. Okay, and again, that's going to cover the material through lecture 7 notes, which we'll complete today, and through these problem sets. Okay, and so we'll have a little be available to discuss your questions at our usual problem session. For at least 45 minutes, we'll have a little review. Okay? I won't come with anything strictly prepared. It's really just about addressing questions that you have. GoPy has problem set 2 graded, so I will look at it and I'll put it in the front office for you to pick up. I'll let you know when that's available, and we'll have the next 2 problem sets. This is just one problem graded as soon as possible. Right? All right. By the way, so the exam is going to be closed book. All right. There's not a lot of formulas, and to remember, it's more conceptual. All right. So just keep that in mind. All right, very good. So last time we had established the fundamental properties of states in quantum mechanics. A state in quantum mechanics, the most general state in quantum mechanics, is described by a density operator, and we typically call that rho. And this operator has some basic properties. It's a Hermitian operator. It's also a positive operator. And we, by convention, normalize it so that it's easy to calculate probability. We can always renormalize afterwards if that wasn't the case. So this is not a fundamental property, it's a property that we impose in order to easily calculate probabilities. And because it's a Hermitian operator, we can diagonalize it, and it has a decomposition in terms of its eigenvectors and eigenvalues. These eigenvalues are all non-negative numbers because this is a positive operator. Okay? So we can always think about the density operator as a statistical mixture of its eigenvectors weighted by its eigenvalues. But as we noted, we should be a little bit careful. We can think about the density operator in an infinite number of ways. If it's for a general mixed state, there are a uncountably infinite number of different statistical mixtures, all of which give the same density operator. There's a unique spectral decomposition up to degeneracies, but as we saw in the homework and we saw last time, we can mix together different pure states and get the same state. Which is to say, if we do measurements, our predictions are exactly the same. We couldn't tell the difference as far as the measurements we would make. That's what it means to say the state is the same. Of course, if it's a pure state, then there is a unique density operator, because there's only one thing in that, there's only one term in this decomposition. Right. Now, we talked about a way of determining whether the state was pure or mixed by looking at something we call the purity of the state. The purity of the state is assuming we have a normalized state given by the trace of rho squared. And so if it's a pure state, this purity is 1, and if it's a completely mixed state, then it has the minimum value of 1 over the dimension of the Hilbert space. And under that case, the density operator is just proportional to the identity. And it looks the same in all bases. For a pure state, it's just a single projector. Okay? One concept we didn't introduce, but I just want to mention, another way we can think about the degree of mixedness of the state is thinking about entropy. Now, you learned about entropy in the context of statistical physics or thermodynamics, but entropy is a somewhat more general concept from information theory. And you can think about entropy as the information I'm lacking about the state of the system. So when something has 0 entropy, I'm not missing any information whatsoever. I have a perfect description. It's perfect, there's no randomness. Okay, there's no missing information. So a state with 0 entropy is a pure state. A state that has more entropy is mixed because I'm missing information. Yeah.
What base is the logarithm?
Well, your choice. So that's a good. I actually by how shall I say it? I purposefully didn't put the base here because it depends. You have your choice what you want to do. If you write this in base 2, then you're measuring the entropy in bits. If you write it in natural logarithm with base e, then there's sometimes called nats. So it's up to you how you want to, what base. It's just a convention that you decide how you're going to measure the entropy. So if this was a 2-state system, that is to say, if it was a dimension 2 Hilbert space, and we measured this base 2, then the maximum entropy is 1 bit, which means I don't know whether it's up or down. Yeah, you had a question.
Well, this has really more to do with stat math.
Uh-huh.
Do you need to multiply it against some sort of constant to?
Right. So if we want to measure it in energy units, or I mean Boltzmann constant is a way of relating the entropy to, in some sense, energy, right? Because the Boltzmann constant times time. That's a convention, but we don't need to do that. We can write it as this is dimensionless. So in some sense, this is a counting argument. Okay, so it's another way to think that I want you to just keep in mind that pure states, again, are states where we have maximum possible information. Those states have 0 entropy. A state that's mixed we're missing information about the state of the system, then it has finite entropy. Okay. All right. Now, we, at the end of lecture last time, talked a little bit about dynamics. And in particular, what we talked about was closed system dynamics. So if we have a closed quantum system and all degrees of freedom are accounted for, and as we've argued before, that evolution must be unitary. Okay? And if I say have the state and know what the state of the system is, I define, or at least this is the state I've assigned based on my information at time t equals 0, then the state at a later time is given by this unitary transformation on the state, as we showed last lecture. Okay? And that kind of evolution is something which preserves the purity of the system. That is to say, as we calculated last time, the trace of the rho squared at the later time, at any later time, is the same as what it was at the initial time. It's unchanged. It's conserved with time. Okay? Equivalently, we could say that the entropy is preserved. Right? Because the eigenvalues are the same at all times. So this is a point that I want to just mention. It's a point of linear algebra that we didn't state before, is that unitary transformations preserve the eigenvalues of an operator or a matrix. Is that obvious? What I mean by that is, let's say I have an operator A, and I do a unitary transformation on it. I can put in the U or U dagger on either side, it doesn't matter. Let's say I do it like that, and let's call this B. What I claim is that both, if A, so let's say A is a Hermitian operator, so is B then, right? And what I claim is that the eigenvalues of this operator are the same as the eigenvalues of this. How would you prove that? Let's see. Anyone have an idea? What do you see?
Look at the determinant of B minus lambda I. So then on the right-hand side, rewrite I as U, U dagger, and factor them out and rewrite it as A lambda I.
You could do that. That would definitely work. We could look at the determinant, and that will work. I'll show you a very quick and dirty way to do it. Let's just say that A is got a spectral decomposition, right? Then what is B? Well, it's that. These are a new set of vectors, but it's the same eigenvalues. Okay, so it's just a quick and dirty way of proving that. So if you do a unitary transformation, you don't change the eigenvalues. And if you don't change the eigenvalues, you don't change the entropy, you don't change the purity. The degree of mixedness is the same. All right. I'm going to scoot by here, so good. Thank you. So throughout, we've talked about, in discussing dynamics, we've restricted our attention to closed systems. Okay? And that, in a closed system, what we're imagining is that we have a description of every degree of freedom in the system, and we can track it. So closed system dynamics every degree of freedom is accounted for. And as we discussed, for quantum mechanics, that has to be described as by a unitary transformation. But maybe in certain circumstances, we don't, or it's essentially impossible to account for every single degree of freedom in the system. That's particularly true as systems become more and more macroscopic. It becomes more and more difficult to do that. And in fact, we're familiar with that in classical physics. For example, when we talk about thermodynamics, which is typically applied to looking at physical systems in the macroscopic world, we imagine the system of interest might be in contact with, for example, a thermal reservoir. or sometimes we call it the bath, right? Because we used to think about it as some, liquid that you immerse things in. And this thermal reservoir might be at some temperature T. And then the system is exchanging, say, energy with the reservoir. And typically we imagine that at some point later this comes to equilibrium. Thermal equilibrium, for example. Now, thermal equilibrium is this kind of steady state evolution is not really, it's an irreversible process typically. And it's not consistent with the microscopic laws of classical dynamics. The microscopic laws of classical dynamics are time reversible. But I think when you shatter chalk at least once a lecture, that's a pretty irreversible thing. Now, it's only, we say, effectively irreversible, for all intents and purposes irreversible, because of the macroscopic nature of the environment. That's another word for this. So the reason that things are irreversible in some sense, we imagine, at least one way of having irreversibility as an emergent property from fundamentally reversible dynamics is if we kind of coarse grain and say that there is sort of, there's the fine-grained microscopic degrees of freedom, but within some coarse graining of the degrees of freedom, things are lost and they're just sort of there so long they never come back. This is, of course, a deep problem. It's a complicated problem. How is there an arrow of time really? More fundamentally, are there things that are fundamentally irreversible, like black holes? Or is information lost behind a black hole? There's, of course, very deep and fundamental questions. However, putting those aside, we could say that we could, even without getting that deep about it, that we can get irreversible dynamics effectively from fundamental reversible dynamics in the macroscopic domain. Okay. And for example, one of the things that could happen in this kind of thermodynamics is, for example, this might come to equilibrium, so I might have had something which, say, once it got in contact with the heat bath, its entropy increased, for example, right? That's a problem I'm sure you solved in thermodynamics. So the entropy of the system isn't conserved. In this case, it would be if I had perfectly reversible dynamics. I would not change in any way what information I had about the system if it was all perfectly looked at every molecule and can follow every one of those trajectories. But if I lose track of it, I lose track of information, entropy increases. Okay? So that's classical. And the same thing would be true for quantum open system dynamics. So whereas if we take account of every degree of freedom that describes the state of our system, that is described by a unitary evolution, if my quantum system is in contact with the environment, I can call it the reservoir, the bath. Right? My quantum system, whatever this is, could be an atom, could be a molecule, it could be a superconducting circuit. And it's in contact in some way with something we'll call the environment. It's a quantum environment. All the degrees of freedom of the environment are themselves also described by quantum mechanics. Then I can get effectively irreversible dynamics here too, in the same way that I had it in classical thermodynamics. And this is not unitary. Because information about my quantum system is being lost to the environment. It ain't coming back, because it got lost in this macroscopic number of degrees of freedom that I call the quantum environment. Okay. So I could get a situation where, my quantum system comes to thermal equilibrium. Like the spins out of the oven, the silver atoms out of the oven in the original Stern-Gerlach-Gedanken experiment that we discussed. I mean, what's going on is the spin is the silver atom is bouncing around, they're colliding with other atoms, and it's depolarizing the atoms, and it's totally random. And I lose information about whether it's spin up or spin down to the collision information that's stored in the other atoms, which provide an environment for any one atom, or the walls of the oven itself, which interact through collisions, for example. Okay, so I can get an increase in entropy. I can get a decrease in entropy. That's called cooling, right? I can change the entropy of the system. So if it's non-unitary dynamics, do not conserve purity or entropy. Entropy, I could heat, entropy increases. I can cool, entropy decreases. Of course, the entropy of the environment increases. And of course, this is one of the ways that you prepare a pure state, or try to. This is by taking a state, some state, and then getting it towards, this would be the ultimate in entropy decrease. Now you can't do that perfectly, that would violate the third law of thermodynamics, but you can get as close as you possibly can by improving the refrigeration. Yeah?
Is it possible to have a physical quantum close to system dynamic? Because if you decrease entropy in the closed system, the entropy outside system must increase to keep it balanced, right?
Right. So if it's completely closed, then entropy is conserved, because then it's unitary. So it's always relative to other degrees of freedom where that entropy is high. Yeah.
Couldn't you, in theory, say that if we know all the degrees of freedom of the universe, then the entropy would just not be increasing?
That's right. I mean, if you were able to track everything, both of the system and the environment, then the whole system, the entropy has remained exactly the same. I mean, that's the same thing true again when I crush the chalk. I've increased the entropy of the chalk right? But of course, that information about how that fractured is stored in all the vibrations of the floor, which ultimately hit the wall and whatnot. And I have to keep track of all of them in order to maintain complete knowledge. But if I say, I'm only going to keep track of these degrees of freedom, and all the rest of the degrees of freedom are effectively lost to me because I either don't want to bother or don't have the ability to keep track of them, then the entropy of this system has increased. The information about that system is lost to what's going on here. Now, there's more in the quantum world than just that about energy exchange and heating and cooling, because we know that when we gain information about a quantum system or lose information about a quantum system, our state of knowledge about the quantum system is changed in a very fundamental way. So, coupling a quantum system to an environment affects our state of knowledge about the quantum system in a profound way. For example, if, suppose at time t equals 0, I have a pure state. If through the coupling to the environment, I have some later state of system which is now mixed, because I've lost information in the environment, for example. If that's the case, then I have lost coherence. In other words, it might be the case that through this coupling to the environment, I might have, for example, let's say for a spin 1/2 system at time t equals 0, we had a pure state, which we said generally has this matrix representation in the basis of spin up and spin down along some axis. That's my pure state. Through the interaction with the environment, I can end up with this state. Where I've lost information about whether it was in a superposition or not. And this process whereby I lose this is called decoherence. Decoherence is a dynamical process completely described within quantum mechanics. I don't need any magic collapse postulate. It's as equivalent in classical mechanics to the approach to equilibrium. I can derive this in a non-equilibrium statistical physics whereby I have some model of the environment, some model of the coupling of the system environment, and some effective coarse graining. That's important. If I don't coarse grain, then I keep track of every last detail, and then I never lose coherence. I have to somehow say that that went away effectively. Okay? So decoherence is describable completely by self-consistently within quantum mechanics in the same way that the approach to thermal equilibrium is described within the context of classical mechanics. This kind of evolution is non-unitary. Now, there's a few other things I would say about this kind of evolution. There's lots of ways of how to think about equilibriums. Well, one way to think about it is that the environment measures the system, but doesn't tell us the result. The environment contains information about whether the spin was up or down, but we don't know. If we could dig it out of the environment, then we'd know which one it is, but we can't do it because it's buried in these crazy molecules going in all kinds of directions. And since we don't know it, it's as if Alice prepared spin up with this probability, or she prepared spin down with that probability, but didn't tell us. For all intents and purposes, it's the same thing. Okay? So, what that means is that the environment prepares a statistical mixture. Another way to think about decoherence in a related way is that the environment does a random unitary. It doesn't tell us, but we don't know which one. So how would we describe that evolution? Well, we would describe that as the following. If it did a particular unitary evolution, let's say the ith one, then the evolution on the state is that, right? But we don't know which one it is. So we have to average this over all the possible, weighted by some probability that it did a particular unitary evolution. Okay? Okay, so this kind of evolution is not unitary, it's a sum of unitaries weighted by these probabilities. In fact, we typically would write this in the following way. Where this operator AI is the square root of the probability of the ith unitary. This is what's called a Krauss operator. This kind of evolution is a map on the density operator, takes the initial state to the final state, but it's not a unitary map. It's a non-unitary map. It's what we call a completely positive map for very technical reasons. But basically, it takes a positive operator to a positive operator. Not a completely positive map. Or a CP map. example, let's suppose I have a spin 1/2 particle. Let's say that spin 1/2 particle was initially polarized along the x direction. Okay? So let's come over here. Let's say at time t equals 0, it is paired along the x direction. Spin up. Okay? And that state we know is a superposition of spin up and down along z, right? Now, suppose that the environment gives a little kick, a random kick to the spin, and kicks its direction by giving a small rotation around the z-axis. Okay, there's some environment that's out there that's just giving it a random kick, and it rotates it about the z-axis by a small angle, some random angle. Okay, so let's say the environment kicks spin and rotates it slightly, or randomly, doesn't even have to be slightly, about the z-axis. Now, what that rotation, action of rotation, we will study that in detail later in the semester, but it's easy to write down. The rotation around the z-axis is defined by a unitary operator. It leaves the up along z and down along z alone. So those are the eigenvectors of this. And the eigenvalues of a unitary operator are phases, right? You remember that. And the phases are, if my angle rotates it around the, say, the z-axis by angle phi. So what we'll find is that this is e to the phi over 2, and this is e to the plus phi over 2. This is the rotation operator. It rotates around the z-axis by angle phi. So let's apply this to our state. So let's say, so my rotation by angle phi on the state. I'll do it in the density operator formulation. Okay. So this is equal to, let's write this out. This is a half up plus a half down down plus a half up down plus a half down up. Plugging in the state. It has diagonal matrix elements and off-diagonal matrix elements, right? So what happens when I apply this operator to this? You guys tell me. What happens to this guy? If I put the U dagger on this guy.
The phase of the
So let's look at this diagonal term first. What happens to this term when I apply this guy? So let's look at that. U dagger.
Pick up the phase.
Yeah, you pick up the phase, but then on the other guy, you get the opposite phase, right? So it does nothing, right? And that's true because this is an eigenvector of rotation around z. It doesn't change it. So the diagonal terms stay exactly the same. But what about the off-diagonal terms? On this guy, you either get e to the minus I. On this guy, you get the conjugate of e to the plus I. Those get the same. So this becomes 1/2 e to the minus I plus minus. Right? And this guy becomes e to the plus I minus plus. The other guys don't change. So written as a matrix, after this little random kick does what? Well, it leaves the diagonal terms the same, but it puts a phase on the off diagonal because we've rotated it. Buy that? So now suppose that I have a random phase. So my actual state at a later time is the average over all phases so I'm going to average this by summing over all the random rotations. What happens to this? I'm going to integrate that over all angles. It's 0. This became a completely mixed state. I started with a maximally pure state, a completely pure state, and I ended up with a maximally mixed state because this state was a statistical mixture of this and 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 this. And all of those states have different phase relationships with respect to one another. And when I statistically average over them, it's as if they have no phase relationship with respect to one another at all. I've randomized the spin. This is what we call dephasing channel, or dephasing, which is another word for decoherence. I've lost the coherence because I lost the phase information about my superposition. All right, so decoherence is a phenomenon. It's a phenomenon that we must take into account when we have a quantum system that is coupled to the environment. And quantum systems are always coupled to the environment. Even the vacuum is the environment. Because the vacuum itself is a quantum thing. And an atom that's in an excited state will decay irreversibly. That is coupling to the open quantum system. That is a non-unitary evolution. And that happens because the vacuum itself is the environment. So, last bit about this. Does decoherence solve the measurement problem? Some people would say it does. Wojciech Zurek up in Los Alamos is one of the key figures who's developed this whole idea about decoherence and how important it is in thinking about quantum mechanics, and there's no doubt it is. Some say decoherence is then the answer to the measurement problem, because I went from a quantum superposition state to a state that's a statistical mixture, and that's what we kind of see. We see these random statistical mixtures. So what do you think? Does decoherence have that? You don't need to worry about the cost of the wave function anymore? Decoherence is the end of the story?
What if you hit the new density operator with the rotation again?
Well, it wouldn't do anything anymore after I've averaged it out, because it does, I mean, the off-diagonal elements are now 0.
Before you average.
Well, then you keep getting random kicks. I mean, it's really, the averaging here is all about lost information. If we keep that information, well, then it's just a rotated spin. Yeah.
So, I mean, we're saying we have random kicks as we don't know, and
Yeah.
the information's in the environment.
Yeah.
I mean, so if we kind of knew we wouldn't sum overall, I mean, wouldn't we still have a...
Sure, we have a quantum many-body state, which has coherence between the thing that did the kicking and the kicky. So, yeah, it's only, the rabbit went in the hat here, where I said, we lost information. I didn't derive that from any fundamental thing. I would say now this is the editorial opinion here, so we'll go into the editorial page. This is not a textbook. Is that decoherence is an important ingredient in understanding measurement. One thing it does is it answers the problem, what is a measurement? A measurement, so it answers the question of Bohr, as we discussed, and the Copenhagen interpretation invoked the classical world. It said that a device performs a measurement if it's a classical measuring device. But it didn't quantify what devices should count as classical and what devices are just other many-body quantum systems that are talking to this little quantum system. What we could say is a device does a measurement when effectively the pointer of my meter is classical. And if that pointer the different quantum states of the pointer have decohered. In other words, I can, for all intents and purposes, never see quantum interference between the different states of the meter, because those off-diagonal degrees of freedom have been lost to the amplifier, to the power source on the grid in P and N. For all intents and purposes, I can't see interference, so it's a classical entity. And so if I can't, just from an operational point of view, if I never see interference between those different alternatives, they are classical. So it, in my mind, answers that piece of the question. What kinds of devices are classical measuring devices? They are the ones where the states of the meter decohere through the measuring process because they're effectively macroscopic. So Bohr intuited that, I think. Understood that what meant for macroscopic. What decoherence doesn't answer is the question, why do I see only one measurement outcome? There's no collapse here. There's still no collapse of the wave function where it's one or the other. It's now in this mixed state. And there is no way to get randomness out of a system which are fundamentally reversible and deterministic without putting it in by hand. And you know, the quantum Bayesians say it's the observer. The Copenhagen interpretation says somehow something random did happen, we just don't know which one it was, and it randomly became this pointer. That's still a mystery, in my view. And it's still something we don't have a self-consistent picture, and we just kind of do a meta. We say something above quantum mechanics, and we just extract it out. All right. Adrian, you had a question about the density operator, the notation, and we didn't get a chance to.
Yeah, actually, so there, the notation is a sum of, the same.
This guy?
Yes, perfect. So it's the sum of the same ket.
Yep.
Can we write it as a sum of different kets?
No.
Okay.
So that kind of state, I mean, it's true that if we look at this, go back over here, please, thank you, that this is a sum over some different kets. But it itself, that sum must collapse to something which is a projector or sum of projectors.
So it'd be wrong to write it in.
There is not a general form. I mean, it's true, we can always write rho in a basis, right? So if I put in a complete set of right, that's a perfectly good representation. So it is a sum, as you say, of different, a Brown-Ket of different weighted, but that sum must collapse ultimately to this.
Okay.
There is no state of the system which is this 5 times psi is not a state.
Would it be okay if it was one of the sums of this? Like what we have?
As long as the sum ultimately collapses to this, then yes. Because as I said, this is a sum. But this is not a Hermitian operator, right? Yeah.
So it would collapse to that only if you put it in the right basis, though, correct?
It would, yes, exactly. You wouldn't be able to see it. Like as you say, this guy doesn't collapse that because in the z basis it has off-diagonal elements, but in the x basis it doesn't. It's hard to tell by the basis. It's better to think about it from basis independent indicators, like is it Hermitian? Is it a positive operator, which if you look at the expectation value, expected should always be positive. You can't always look at the sum and see it. All right, so to conclude this, I want to say, we have talked about for weeks now the postulates of quantum mechanics, and we started with the Copenhagen interpretation, and we kind of modernized Copenhagen. So I want to state for you what I would consider to be the modern postulates of quantum mechanics, which are unfortunately not written in your standard textbooks on quantum mechanics because they're old. So I'll write them in sort of two, so I'll write them with in the Copenhagen way and modern. States are vectors in the Hilbert space. I'd say the modern thing is that a state is a positive operator. Bro. Measurement outcomes occur with probability p T A given by the square of the amplitude, where A is an eigenvector of observable A. What I would say is a measurement is described by a POVM, which is a set of positive operators which sum to the identity, such that the probability of outcome mu is the trace of rho within mu. These are generalizations of these. And then we have one final thing, is about dynamics. General dynamics of the state closed system that's Copenhagen. Modern would say the closed system rho of t evolves according to unitary transformation. And finally, generally, a CP map, which is that rho of t is given by a sum of Krauss operators acting on the state conjugated to that, where they're not unitary. And post-measurement state. If we find A we collapse. That's Copenhagen. Modern, the post-measurement state is given by a particular Krauss operator associated with that operator acting on the state remoralized. You now know all of quantum mechanics, pretty much. There's maybe one other possibility you might say something about multiple degrees of freedom and tensor products, but we'll get to that. Now, I note that the modern thing that I broke down is devoid of physics. It says nothing about the physical world. It doesn't say anything about Hermitian operators. It doesn't say anything about observables. Where the heck is the physics? This is physics, for God's sakes. Well, what it's saying is that this framework here is a kind of information theoretic framework, and it's a framework that has developed in quantum information science, which is my subject of interest and research, but it tells me that there are parts of quantum mechanics that in some sense are about information theory, that aren't really even about physics, just about how we know things about the world and how we make predictions about the world, not about the nature of the world as the physical world as it is. And we want to now, finally, 1 month and a day after, say, how does this stuff connect to physics? And that's where we're going to begin now. So how do we hook this information theoretic foundation onto the physical world? So the way we're going to do that is through something called Noether's theorem. Now Emily Noether was a physicist in 100 years ago, who was studying at that time classical mechanics. But the Noether's theorem is very profound and important. And what Noether's theorem tells us is the following: that to every physical symmetry is associated a conserved physical quantity. So there's an intimate relationship between symmetries and conservation units. This is something that can be derived from Lagrangian mechanics. You guys derive that in your classical mechanics? Did you ever see that? You might have seen some parts of it. And then there's a connection here to mathematics, which is that symmetries, the set or symmetry transformations are groups. And in particular, what I should have said physical continuous symmetry is important. I'm talking about a group of objects which are continuous. These are Z groups. That the conserved quantities are the generators of the group. Let me explain what all this means. So, what are some examples of conserved quantities? Physical quantities. Energy. Momentum. Angular momentum. These are associated, these are conserved in nature because the universe has certain symmetries. because we believe that fundamentally the universe is this, its overall properties are the same at any point in time. The properties of the universe are the same properties. That's debatable. We can ask whether the fundamental constants are actually changing in time. But to the degree to which we believe they're not, this is related to time translation and variance. Overall, I mean, of course, we can have local variations, but overall, the laws of physics we assume are the same, no matter what point in time we're at. Momentum is conserved because of spatial translation and variance. That is, the laws of the universe are the same at any point in any place in the universe. And angular momentum is about rotational invariance. The universe is, at some level, isotropic. So what this says is that each one of these symmetries is associated with a conserved quantity. These symmetries themselves are groups of transformations on space and time. And the generators that generate those transformations, what I mean by a generator, I'll explain in a moment, are the energy, the momentum, the angular momentum. So the connection here to the quantum theory is about the generators of symmetries and the symmetries themselves. So let's talk about that. So let's talk about groups. Let's remind ourselves what a group is. So a group is a mathematical construct. So this is a set with a composition law. So we have some set of objects. Let me just call them lambda. And there's a composition law such that if lambda 1 and lambda 2 are in the group, then if I have some way of composing these two together, this is also in the group. Okay. It has one group, we have an identity element. Such that if I compose this with the identity in either direction, I get the thing back, and it has an inverse. Such that if I compose this, I get the identity. Okay. Yeah.
Isn't there a fourth that's like associated with you or something?
Yeah, that's right. It's also an associative composition indeed. Okay, so this is a group, and in particular, it could be a Lie group if this set is a continuous kind of differentiable set. I'll just loosely say that. If ran like points on the line through addition. So, how are we going to connect this to quantum mechanics? Excuse me, Stephen, let's scoot by in here.
the elements of our group are to be functional?
No, what we're going to do in a moment is let me explain what their elements are. So, Wigner talked about the theory of symmetries in quantum mechanics. We're going to talk about this in great detail, some amount of detail next semester. So let me just begin this. So, what this is in quantum mechanics, we represent the group by unitary, actually, or anti-unitary. We haven't described anti-unitary, but we'll get to them. They play minor role operators. What do I mean by that? Well, what it says is that I can, for every element in the group, I associate a unitary operator depending on that element. And this is a representation of the group if the operator composition of the two is just that. Okay? So this is what we call a group representation. So the elements of the group are unitary operators now. And everything that was in G is now a U depending on that. Okay? And so, for example, the U for the identity operator is just, not unit, for lambda equals 1, is just the identity operator. And U of the inverse is the inverse unitary, which is the adjoint. So this is a representation of the group. Yeah?
Can you always make a unitary representation, or does that only apply to specific?
No, you can always do that if they're groups.
It's like groups.
You can always represent them by matrices, but not unitaries. Yeah. All right, so now if it's a Lie group and there's this notion of differential continuity, we could have what we call near identity. Okay, so this is the identity. I'm going to have something that's close to the identity in the sense of I go a differential distance away from it, or a small distance away from that. Okay? So, let's say I have some unitary, which is the identity involved or composed with some small, epsilon is in some sense small, close to the identity. This is equal to, I claim, the identity operator plus that epsilon times an anti-Hermitian operator. How do I prove that? So this is, let's say this is the group under addition. What do we have to prove? Well, we have to prove that the composition law works. And we have to prove that the inverse is the adjoint. Okay? So, let's do the composition between two of these. Well, that's trivial. That works. This is U at the thing that's close to that sum. That's fine. The composition law obviously works because it was addition. The inverse, according to the addition law, would be minus epsilon. So that's equal to 1 minus epsilon A. But A is anti-Hermitian. So minus A is A dagger. So this is equal to that, which it must be. So this is a way of representing the elements of the group near the identity. And this A is known as the generator of the group. Now there may be, if I don't have a one parameter group, if I have a multi-parameter, then I'll have more than one. This would generally be a vector, and I have a vector of possible generators. But for the moment, let's talk about a one parameter group, like translation in time, or translation along one direction of space. Okay? Now, by convention, we write A as minus I times a Hermitian operator. So that the near unitary, or near identity, excuse me, all right, finally, let's say something about this connected to physics. Let's talk about, in the last 2 minutes, and then I'll quit, time translation. So we want to translate the system in time from some initial time to some later time. Okay? And those time translations are parameterized by all the times along the real line. Okay? So, we would say that the group here is defined by a unitary operator parameterized by that element of the group, where I'm going to fix the initial time. That would just be some agreed to. Okay? This is my time translation operator. Let's talk about the near unitary. I'm sorry, near identity. So let's say that we go just a differential time away from t0. Okay, so this is near identity. If I didn't do anything, if I didn't translate by any amount, this would be the identity operator. But I'm translating by a tiny amount. This, according to this, is the identity operator minus I times something which I'm going to call omega dt. Why am I calling it omega? Because this has the units of times to the minus 1. It's a Hermitian operator. It has to be. Now, what is that operator? Well, according to Noether's theorem, the generator of time translation is the thing that's conserved. And what is that? Energy. So that means that this operator has to be proportional to energy. And that energy operator is an operator we call the Hamiltonian. So there's some constant here. It has to be that. So that this thing, so alpha has the dimensions of energy or alpha has the dimensions of alpha are equal to 1 over energy times time. This has the units of 1 over time, and this has the cancel units. Okay? This thing, energy times time, is in classical physics what we call action. Now, what that constant is not given derivable. It's just given by nature. Anyone guess what that unit of action is?
Planck's constant?
Yeah, Planck's constant. Hooray, we finally get h bar.
Wait, shouldn't it be h instead of 2 pi?
No, it's h bar. That's the constant that appears here. It's the constant which allows us to translate the physical quantities of energy and time into Hilbert space units. And so we have that the is the identity minus I over h bar times the Hamiltonian dt. And we have finally written down the Schrödinger equation. And we will continue with this next time. Okay. Symmetries, conservation laws. That's the hook. That's a good, I actually, by, how shall I say it? I purposefully didn't put the base here because it depends. You have your choice what you want to do. If you write this in base 2, then you're measuring the entropy in bits. If you write it in natural logarithm with base e, then they're sometimes called nats. So it's up to you how you want to, what base. It's just a convention that you decide how you want to measure the entropy. So if this was a two-state system, that is to say, if it was a dimension 2 Hilbert space, and we measured this base 2, then the maximum entropy is 1 bit, which means I don't know whether it's up or down. Yeah, you had a question.
Well, this has really more to do with stat math.
Uh-huh.
Do you need to multiply it against some sort of constant to?
Right. So if we want to measure it in energy units, or I mean Boltzmann constant is a way of relating the entropy to, in some sense, energy, right? Because the Boltzmann constant times time. That's a convention, but we don't need to do that. We can write it in this is dimension less. So in some sense, this is a counting argument. Okay, so it's another way to think that I want you to just keep in mind that pure states, again, are states where we have maximum possible information. Those states have 0 entropy. A state that's mixed we're missing information about the state of the system, then it has finite entropy. Okay. All right. Now, we, at the end of lecture last time, talked a little bit about dynamics. And in particular, what we talked about was closed system dynamics. So if we have a closed quantum system and all degrees of freedom are accounted for, and as we've argued before, that evolution must be unitary. Okay? And if I say have the state and know what the state of the system is, I define, or at least this is the state I've assigned based on my information at time t equals 0, then the state at a later time is given by this unitary transformation on the state, as we showed last lecture. Okay? And that kind of evolution is something which preserves the purity of the system. That is to say, as we calculated last time, the trace of the rho squared at the later time, at any later time, is the same as what it was at the initial time. It's unchanged. It's conserved with time. Okay? Equivalently, we could say that the entropy is preserved. Right? Because the eigenvalues are the same at all times. So this is a point that I want to just mention. It's a point of linear algebra that we didn't state before, is that unitary transformations preserve the eigenvalues of an operator or matrix. Is that obvious? What I mean by that is the state is the same. Of course, if it's a pure state, then there is a unique density operator, because there's only one thing in that. There's only one term in this decomposition. Right. Now, we talked about a way of determining whether the state was pure or mixed by looking at something we call the purity of the state. The purity of the state is assuming we have a normalized state given by the trace of rho squared. And so if it's a pure state, this purity is 1, and if it's a completely mixed state, then it has the minimum value of 1 over the dimension of the Hilbert space. And under that case, the density operator is just proportional to the identity. And it looks the same in all bases. For a pure state, it's just a single projector. Okay? One concept we didn't introduce, but I just want to mention, another way we can think about the degree of mixedness of the state is thinking about entropy. Now, you learned about entropy in the context of statistical physics or thermodynamics, but entropy is a somewhat more general concept from information theory. And you can think about entropy as the information I'm lacking about the state of the system. So when something has 0 entropy, I'm not missing any information whatsoever. I have a perfect description. It's perfect. There's no randomness. Okay, there's no missing information. So a state with 0 entropy is a pure state. A state that has more entropy is mixed because I'm missing information. Yeah.
What base is the logarithm?
Well, your choice. So your the one problem from problem set 4 is due today, but there won't be another problem set assigned today or next week because we have an exam coming up, and so that exam again is going to be in the evening offering snacks from 5:30 to 7 p.m. in room 190. Okay, and again, that's going to cover the material through lecture 7 notes, which we'll complete today, and through these problem sets. Okay, and so we'll have a little be available to discuss your questions at our usual problem session for at least 45 minutes. We'll have a little review. Okay? I won't come with anything strictly prepared. It's really just about addressing questions that you have. GoPy has problem set 2 graded, so I will look at it and I'll put it in the front office for you to pick up. I'll let you know when that's available, and we'll have the next 2 problem sets. This is just 1 problem graded as soon as possible. Right? All right. By the way, so the exam is going to be closed book. All right. There's not a lot of formulas, and remember, it's more conceptual. All right. So just keep that in mind. All right. Very good. So last time we had established the fundamental properties of states in quantum mechanics. A state in quantum mechanics, the most general state in quantum mechanics, is described by a density operator. And we typically call that rho. And this operator has some basic properties. It's a Hermitian operator. It's also a positive operator. And we, by convention, normalize it so that it's easy to calculate probability. We can always renormalize afterwards if that weren't the case. So this is not a fundamental property, it's a property that we impose in order to easily calculate probabilities. And because it's a Hermitian operator, we can diagonalize it, and it has a decomposition in terms of its eigenvectors and eigenvalues. These eigenvalues are all non-negative numbers because this is a positive operator. Okay? So we can always think about the density operator as a statistical mixture of its eigenvectors weighted by its eigenvalues. But as we noted, we should be a little bit careful. We can think about the density operator in an infinite number of ways. If it's for a general mixed state, there are a uncountably infinite number of different statistical mixtures, all of which give the same density operator. There's a unique spectral decomposition up to degeneracies, but as we saw in the homework and we saw last time, we can mix together different pure states and get the same state. Which is to say, if we do measurements, our predictions are exactly the same. We couldn't tell the difference as far as the measurements we would make. That's what it means to say